Okay, the next topic we're trying to talk about is the performance issue of RDT. And as we mentioned before, right here, I think it's right here. When we talk about different version of RDT, basically they follow its mechanism called stop and wait. That means sender sends one packet and then it will wait for receiver's response. The sender cannot send two data packets to the receiver without receiving an ACK. So sender send and go to the waiting state, and the receiver send ACK back to the sender, and the sender will continue to send the next packet, and so on and so forth, so on and so forth. But basically, we call it stop and wait mechanism. Okay, so RDT 2.03, 1.023, they are all stop and wait mechanism. But stop and wait mechanism has a very, very poor performance. Oh, okay, so that is the reason why. So let's take a look at this figure. Okay, so let's see. Okay, left-hand side the sender. So at time 0, okay, sender will send D0, right? Send D0 to the receiver. And this dotted purple line, okay, that is D0's first bit, right? It needs to propagate among the transmission link and will be received by the receiver, right? So right here, this part, we can say that is the propagation delay, right? And as we assume that there are the total L bits in D0. So right here, this one is the D0's last bit, right? And among within them, there are total L bits, right? So right here, this part, okay, that is L over R. That is the transmission delay. When we send L bits on a RB per second link, right? So the total time we need to push all those L bits to the link is L over R. So that is the transmission delay. Okay, and we mentioned it before. Okay, when there's a small packet sent from the sender and there's another response small packet sent back from the receiver, okay, so that is the, so actually that is A0, right? That is X, that is X0, right? We assume X0 is a very, very small packet, so we can ignore the transmission delay of X0, but it still needs to take time to transmit from the receiver side to the sender side, right? So we mentioned it before. If we send a small packet from the sender to the receiver and the receiver send a very small packet from the receiver back to the sender, and this time is called round trip time, RTT. So in this case, we can see that here is a line right here, right? So total, it is L over R plus RTT. Within this time, L over R plus RTT. With this time, because of the stop and wait mechanism, the sender cannot send any further packet. That is D1, D2, D3, D4 in this time. Server can only send a D1 after it receives X number 0. Right? So sender has to wait. Right? So in this L over R, it's right here. In this L over R plus RTT. In this time, only this portion of time, L over R, is useful. That means we can transmit packet, right? So in this case, of course, you can use any numbers in this formula, but we can see that the utilization of this link is very low, right? Because the sender has to wait a very long period of time, which is caused by the RTT. And in this time period, the sender cannot send D1, right? So as a result, RTT 3.0 protocol, the performance sticks. Okay, so that is the problem of RTT 3.0. Although we can, it is a relatively easy mechanism, so that we can send and receive packet. We have sequence number, we have retransmission mechanisms, we have checksum mechanism, something like that. But the performance is very poor because RTT time is quite long. We have to wait. So after that, we have a new mechanism called pipelined protocols. And you can see that at the left hand side, if we have only one packet and we have to wait for the next act, right? But you can see that at the right hand side, if we use a pipeline protocols, we can send a bunch of packets in the pipeline, okay? Multiple packet. And for the receiver, it can send multiple act packet back to the sender. But in order to support such kind of pipeline mechanism, we need some other new algorithms, some new finite state machines, okay? And we use this word called in-flight. The senders allow multiple in-flight not to be yet acted packet in this pipeline. So in this case, we have more packets, so we should have we should have a larger sequence numbers, okay? And as a result, because lots of packets are in flight, right? So just in case, okay, some of the packet, of one or two of the packet in the in flight may get lost or has something wrong with the bit errors, the sender should keep a buffer to store all the in-flight data packet, just in case some of the packet may get lost or may have bit error. So we need to buffer those packets. Okay. In the following hour, we have two different pipeline protocol. One is called go back N. The other is called selective repeat. Okay. We will talk about it later. So let's take a look at the utilization when we use pipelining. So again, here we have several packets, right? So that's D0, right? And that's D1, D2, and of course, so we can send a lot of different packet, right? So in that case, that is the D0s. Okay, let's use another index. Okay, that is D1, D2, D3, so on and so forth. So right here, that is D1's first bit, right? Okay, so that is again D1's last bit. So after, at this blue point, after the receive get the last D1's bit, okay, it can send ACK1 back to the sender. And we assume that the ACK is quite small, so you simply just use one single line right here. Okay, and take a look at this moment. Okay, after the sender get ACK number 1, right? It can further send next packet out, right? So we write it, we write it in this way, okay? You can draw it right here. You simply just write another line right here, and we assume that is dk, that is the kth packet sent by the sender. Okay, and at this red point, it happens to be the last bit of dk. So we draw it in this way, right? So right here, that should be dk plus 1, right? So at the red point, the sender received egg number 1, and at that moment, the last bit of dk has been sent. So in this case, right here, we can say that when we use pipelining, at most, there will be k packet in flight, right? And at the red moment, we receive egg number 1, so we know that, okay, data number 1 has arrived, right? So, and then we can send data k plus 1 to the receiver. So by using that, so you can say that after we receive an egg and we further send the new packet out, we receive the egg number 2, and we will deliver, we will send data k plus 2, and so on and so forth, so on and so forth. So in the long run, we will not waste too much time, even if we have a large RTT, because in this RTT, we continuously send the following packet to the pipeline. So the receiver will continue receiving new packet. So in this case, in the long run, the utilization of such kind of pipelining is nearly 100%. Of course, that is a very simplified example because we have no transmission error, no bit error in these cases. The utilization can be nearly 100%. Okay, but it is just an example to show you that pipelining is truly can increase the utilization of the sender and the receiver. Okay, so that is the math. Okay, again, right here, we'd like to talk about the first pipelining algorithm called go back N. So here's the sender right here. Here's the sender. Okay, so the sender. Let's take a look at this figure. Okay, we can see that we have different colors right here. So in this case, we have the senders. Okay, I have several different segments wait to be sent. So here's segment number 1, segment number 2 to segment number 23. Okay, in this case, okay, as a sender, okay, we have already received egg number 6. So for segment number 1 to segment number 6, they are green. They are in green, right? They are already active segment. Okay, after that, we can see that there are several yellow segments. Those segments are segments that has been sent but not yet acted. That means segment number 7, 8, 9 to 14, as a sender, we already sent those packets to the pipeline, but we have not get the acknowledge back yet. Okay, so that is the definition of a yellow segment. And here we have some blue segment. That means layer 7 has already sent those messages, and we segment those segments, right? So it's number 15, 16, 17 to 20. But as a sender, they are in our queue, but we are waiting for some moment to send all those segments to the receiver, but we have not yet sent those segments, so they are in blue. Okay, so for segment without any color, that means as a sender, I have to buffer all those segments that I already sent and I am planning to send, which is 7 to 20. So the size is big capital N. Okay, so currently it is 14. Okay, so I have a buffer. The buffer can include 14 segments, and part of the segment, they are in yellow, they are sent packet, and part of the segment in this window size, they are in blue, they are waiting to be sent. Okay, and in actually this N number, this big capital N should be larger, but for it's an oversimplified example, so the big N is 14. Okay, and 21, 22, 23, they are segment. Layer 7 protocols may want to send more message, but as a layer 4, we have only limited buffer. We cannot buffer all of the segment, right? So currently I have only 14 slots. So we will reject packet messages sent from the layer 7 if my buffer is full. Okay, so that is the definition of this color. Okay, and in addition, we have two numbers, two pointers. The first one is send base. It always points to the first segment in this window. Okay, the other is next sequence number. It always points to the next packet the sender will send to the receiver, which is number 15. Okay, let's take a look at an example. Okay, so what if we receive egg number 7 at this moment? Okay, if I receive egg number 7, that means, okay, the receiver has already received data number 7, so I can move my window to next slot. And as I mentioned before, the pointer send base should always point to the first segment. So it should point to number 8 right now. And since the yellow segment number 7 has been active, so it should be green right now. So we draw it in green, right? So at this moment, if the upper layer 7, they indeed send the new messages. So the new message will go to segment number 21 if there is new message waiting to be sent. And that is the definition. How did you move this window to the next slot? Okay, but there's a very interesting thing right here. In go back N mechanism, there's a very interesting rules that they use. The go back N uses cumulative egg. Cumulative egg means X all packets up to including sequence number N. Okay, let's again. If at this moment we receive egg number 9, and egg number 9 means the receiver has received all the packet before number 9, including number 9. So at this moment, the sender knows, okay, I received egg number 9. So basically we can move the packet to here because number 9 and all the packet before number 9 has already been egg. That is the definition of cumulative egg. So we can draw it again to the green one and point the send base to the first segment in this window, which is number 10. So make sure you understand the definition of cumulative act, because it is more convenient for receiver to send only one packet to indicate that multiple packets, data packet has been received by the receiver, right? Because, for example, I can send act number 13. That indicates packet number 10, 11, 12, and 13 has been received by the receiver. But I only need to use one single cumulative act number 13 to indicate that. That is more easily that is more convenient to do such kind of acknowledgement with using less acknowledged packet. Okay. Next one is the timer. Since we know packet might get lost, so every time when you move the window, you simply just set a timer at the oldest in-flight packet. Actually, it means the first yellow packet. The first yellow one. Every time when you move the window, take a look at the first packet. If it is a yellow packet, and you set a timer for this yellow packet, because this packet is the oldest one, and it might get lost or something like that. You only need to set one timer, because there's an interesting thing right here. If this oldest timer times out, and then we retransmit packet N and all higher sequence packet in the window. In other words, that means all yellow packets. If timer number 10 times out, then in this case, we will send packet 10, 11, 12, 13, and 14. That means all the yellow packets in this window will retransmit all the packets. So that is the reason why this algorithm called go back N, because at the most there will be capital N packet will be retransmitted if all the packet in the window is yellow packets. And if the first packet times out, then we will retransmit all the capital N packet in the window. So that is the go back N. Okay, so let's take a look at the receiver side. Okay, again, at the right hand side, I put the sender's view right here. Make sure you understand that. Okay, but for receiver, it is more easily to understand. Okay, you can see that the only thing that the receiver in go back N need to remember is the next accepted expected sequence number, which is RCV base. For a receiver in go back N, you only need to remember what is the expected sequence number you would like to receive. So for example, right here, the receiver view of sequence number space is right here. So as you can see that the pointer is right here. That means the receiver has already received data 1, 2, 3, 4, 5, and it already act 1, 2, 3, 4, 5. So it is waiting for data 6. But you know, as the sender, the sender sends those packets pipelining in the pipeline, right? So number 6, 7, 8, 9, 10, and 11, 12, they may come consecutively, but there's always something might get wrong, right? So in this case, we know that data number 6 is not received, so it is in gray. But data 7, 8, and 9 arrives at the receiver side. Okay, so that is the definition of this is red segment. Okay, if data 6 just the data 6 just queue in the buffer, so after the conjunction the packet arrives and then it's fine, we have 6, 7, 8, and 9. But if the packet get lost in the routers, the timer at the sender side will eventually time out. So for the go back and sender, it will send 6, 7, 8, and 9, and possibly 10, 11, 12. Send all the packet, yellow packet in the window to the receiver. So eventually, no matter how packet number 6 experienced, the receiver will eventually get D6, D7, D8, and D9 again. Right, so that is how they do pipeline and retransmission. Okay, but there's one interesting thing right here is that when the receiver get the out of order packet, okay, it has two different implementations. The one is to discard D7, D8, and D9. Don't buffer them. And the second implementation is, okay, I can buffer D7, 8, and 9. It depends on the different implementation, which is okay. Because no matter what, when the timer of T6 times out, all the packet in yellow, which is 6, 7, 8, and 9, possibly 10, they will retransmit again. So as a receiver, you will get 6, 7, 8, 9 again, no matter if you discard the previous 7, 8, 9, or you buffer number 7 and 9, 8 and 9. It really doesn't matter. Okay? If you get 6, and then you can see that the client will send ACK number 9 to the server, to the sender, because it indicates that I already received all the packet before 9 and include 9. Okay, and of course at this moment we will move the receive base to the new expected sequence number, which is 10, for example, right here. Okay, so that is how go back N sender and the receiver works. Okay, so here again, I'd like to show you some example right here. Okay, so now you know how this window works, right? So at the first place we have a window size is 4, and we send the first 0 packet, 1, 2, 3, and at this moment all the packet in the window is in yellow, right? That is send packet, but we cannot send more packet because the window size is a little bit too small, but it's okay. And at the right hand side we can see that we receive packet 0, send packet X0, receive packet 1, send X1, and receive packet 3 because packet 2 get lost. And in this implementation right here, okay, this implementation has no buffer, so it chooses to discard packet number 3. And in this moment, it's very important. Since we use cumulated ACK, at this moment, we cannot send ACK number 3 because ACK number 3 means 3210 are safely arrived at the receiver side, but we lost packet 2, right? So currently we can only send ACK number 1. So even if ACK 0 goes back to the sender. So we can move our window, right? So when we move our window, we can further send packet 4. And again, we receive ACK number 1. So we can again, we move our window and send the next packet number 4 and number 5. So even we have number 4 and then number 5 arrived to the receiver, we can simply just discard it and resend the ACK number 1 until, okay, as we mentioned before, when we move, it's right here, when we move the window, right, you have to set up a timer, which right here is T2 right here. So when you move your window to first packet, to packet number 1, you need to send T1. Okay, when you send packet 0, you have to send a timer. Okay, but when you send packet number 1, you don't have to send. I do have to set a timer for T1 because at that time T0 has been set, and in entire window only one timer for a window. So after that, we can see that in this time period, we did not receive any ACK 2, right? Because packet 2 has been lost. So when timer timeout, we can see that is go back N. Because we will send all the yellow packet in the window, which is 2, 3, 4, 5. And again, right here, after we receive those packets, we will deliver this packet and we'll send the corresponding X back to the sender. So that is how go back N works. Okay, and again, in this textbook, okay, we do have go back N finite state machine, but it is not right here. So you have to go back to the end of this slide. It's right here. So let's take a look at the go back N's finite state machine, and I think it is again not that difficult to understand the finite state machine. Okay, so please follow. Okay, follow me. Okay, you can see that so now at the right hand side, you know what the blue, yellow, and green segment means, right? So the green segment means all the packet has been acted, okay? And we have a size of window N, capital N. Part of the segment are sent but not acted. Part of the segments are waiting to be sent. And we always set the timer, real timer, at the very first yellow segment in this capital N. So right here we have the first, okay? So right here you have to take a look at this if and else, okay? When we get MSG from the layer 7 protocol, right? Okay, so take a look at this one. If next sequence number, which is the blue pointer, less than base is the yellow pointer, plus N means the size of this black window, right? If next sequence number is less than base plus N, base, so let's use, base is right here, right? Base is right here, plus N is right here, right? So that means the blue pointer is less than the last segment in this N, right? In other words, that means we has blue in N. Okay, sometimes if all the segment in this N window, sometimes there will be all yellow segments. It is possible. Okay, it is possible. That means all the packets of n are in flight, so we don't have more room to send additional in-flight packet to layer 3. Sometimes if that means we don't have any blue segment in the n window because all the segments are in yellow. So in this case, the if else, the if means if there's still has blue segment in n, so then we do this part. The else means has no blue. That is all yellow. Right? If all yellow, then we simply just refuse the message you sent from the layer 7. That is because we don't have enough room to send additional segment to the internet. Okay, so right here, if we still have blue segment, then we send that blue segment. So right here, we send the segment pointed by next sequence number, this pointer. Okay, but right here we have a very strange thing. It's right here. If base equals to next segment, if base segment equals next, so if base pointer equals to next segment number, that means all the segment in this n are all blue. So that is all blue. All blue means I want to use the first blue segment to send this packet out. So I need to set up a timer right here for the first non-blue segment, because next statement right here is next segment. We plus 1 on the next segment number. So that means we have first yellow segment. So for the first yellow segment, we will start a timer for this first yellow segment. Right? But if you move the window and there's a still yellow segment in the window, then we don't have to set a new timer. We always set a new timer for the first yellow segment. Okay, so that is step number 1. Okay, step number 2, if timeout occurs, and then this part is that is go back in. If timeout, and then I will set another timer for the first yellow segment in the window n, right? And then we will send the first yellow segment, the second yellow segment, until the last yellow segment. The last yellow segment will be pointed by the next sequence number -1, right? Because next sequence number is the first non-yellow segment. So -1, that is the last yellow segment. So that's all yellow segment will be retransmitted. So that's number 2. Okay. Number 3, as a sender, when I receive a packet and it is not corrupted, so I will take a look at the sequence number that I received. The ACK number that I received. Take this, for example, that is number 5, for example. If I get ACK number 5, then I plus 1, so that is number 6. That means I will move my window from the current position to the next position, which is 6, right? For example, for this example, I have 4 acknowledged green packet, and currently I receive the 5th acknowledgement, and then I will move my base to the 6th slot, right? So that is the reason. Okay, so right here again, if base equals to next sequence number, that means this one, the upper one means no yellow. No yellow means all blue, right? The else condition means has first yellow, has yellow. Okay, so you have to set up a new timer for the first yellow segment. And for the upper part, if base equals to next sequence number, that means when you move the window, there has no yellow segment left in the N window, so you don't have to set up any timer because they are all blue segments. Okay, number 4. When you receive a packet but it is corrupted, that means you don't know anything about it. So as we mentioned before, for go back and you simply just ignore such kind of packet because all the retransmission mechanism relies on this timer right now, not on the acknowledgement or any packet we receive. You only retransmit packet as a sender, okay? You only retransmit packet when timer timeout. So step number 4, when you receive any other packet, you just ignore them. Okay, for number 5, that is quite easy because in the first place, okay, that's the initial state. You set the base number to base pointer to the first segment and the next sequence number to the first segment. So that's it. That is very easy. I think that's very easy to understand that. As the senders finite state machine, as a receiver, it is even easier. As I mentioned before, for go back and as a receiver, you only need to remember what is your next expected sequence number. So right here, for step number 1, as a receiver, when you receive a packet and the packet is not corrupted and the sequence number is what exactly you expected, then everything is fine. So you extract the packet, you deliver the packet, and you send the egg using exactly the same expected sequence number back to the sender. That is quite okay. And then you, of course, you have to add 1 on your expected sequence number because that is what you expect next time, right? So sequence step number 1 is quite easy. And again, for step number 2, for any other event, the received packet is corrupted, or the received packet you cannot specify its acknowledgement number, or the acknowledgement number is wrong. Okay, any other event, you simply just resend the purple packet, which is the previous acknowledged packet, and you send the acknowledgement again back to the sender to notify that it is a duplicated act. I don't know what exactly the data you sent before, so please retransmit again. So that is step number 2. And that's all. For a go back and receiver, only 2 different events. One is okay, then I send the corresponding egg. Add 1 to the expected sequence number. For all the other unknown event, I simply just resend the previous purple egg packet. Then to notify the server should do retransmission. So I think these 2 finite statement is easier for. I think it is still easier for you to understand the mechanism behind go back. And so please still take some time to go through the finite state machine again, okay, to make sure you understand how it works. Okay, that is go backend. Okay, we stop right here. So I think next hour we'll talk about another pipelining mechanism called selective repeat. But I think go backend is somehow very, it's not that difficult to understand. Okay, so make sure you understand all the things.